is, let's go 2018, number 1. All right, so this question I think is pretty straightforward. So what I want to do is kind of talk about the background knowledge that you need to know in order to answer this. So we have a spacecraft that's orbiting the Earth, and then they ask us a series of questions about this situation. So this problem falls into Newton's law of gravitation. So what we have is we have the Earth here. Here's the Earth, and then here's the spacecraft, and the spacecraft is in a circular orbit. So let's call Earth mass 1. Here's the spacecraft. We're going to call this M2. The idea here is all objects in the universe attract one another. And then that force is a gravitational force of attraction. So hopefully what I'm doing right now is going to set us up to answer every question. This should be a pretty quick problem. So focusing on the spacecraft, this is spacecraft. If we sum the forces for this spacecraft, so let's sum forces focusing on the spacecraft, the only force we have is the gravitational force of attraction between the Earth and the spacecraft. And then sum of forces always equals ma, and this is a circular path. The spacecraft is in a circular path, so the acceleration is going to be centripetal. And this m right here is going to be the mass of the spacecraft, because that's what we're focusing on. We summed the forces for the spacecraft. So starting with this, now we can plug in equations. So there's an equation for the gravitational force between two objects, and that equation is big G, which is the gravitational constant, not to be confused with lowercase g, which is acceleration of gravity. This g right here is it's 6.67 times 10 to the negative 11, I believe. It's a very small value. So big G, m1, m2 over r squared, where r, and this could become important in other problems. Notice in this problem here, they defined r from center of Earth basically to center of spacecraft. R is always from center to center. All right, so we did this, that's that equation, and then we're plugging in m2. Now, centripetal acceleration is v squared over r. At this point, one of the r's cancels, r drops there, and then m2 also drops out. So I'm just gonna rearrange this. Let's solve this for v squared. So v squared equals g mass of Earth, which I called m1, but you know what? Now let's use their terms. They say right here, the mass of the Earth is me, so let's just switch m1 to me, so we're using their variables. Although don't do that on the AP test. Don't switch variables midway through. I should not do that. And then over R. So this is going to answer most of the questions here. So let's go to the questions. In the figure below, draw and label the forces, not components, that act on the spacecraft. All right, so here's the spacecraft. The only force we have on the spacecraft is the gravitational force. So I would just draw that, label it FG. Boom, we're done. Okay, part B. In fact, I'll leave that there for now. Part B, derive an equation for the orbital period of the spacecraft. Okay, so let's just talk about period. Period is the time for one cycle. There are different things in physics. In fact, the third problem we're going to look at today, which is number 5 on this same year, there's different problems that involve period. So what are the situations that involve period? And again, period, what period is, it's the time for one complete cycle, which in this case, the cycle is the spacecraft orbiting the Earth. So what involves period? Situations that involve period, circular motion, like this. This is what we're doing right now. What else? Where else will you see period? You'll see period with pendulums. You will see period with mass on a spring, a mass going back and forth, mass on spring. And then lastly, you'll see period when it comes to waves. We can talk about if you have a wave like this and the wave is moving past a point, if you're talking about period, it's the time for one full wave to pass you, you know, from peak to the next peak. Okay, so we're deriving an equation for period. We're going to start with this right here. In fact, let me shrink this, and we're going to pick up with what we've done already. Okay, so the only way to get period in here is for an object in a circular path. So let's look at the spacecraft traveling around the Earth. This spacecraft has a linear velocity. You know, like if the spacecraft suddenly left the circle, this spacecraft would have a velocity measured in meters per second. You know, so you can imagine yourself running around like a circular track. If you wanted to find your velocity, not angular velocity, but linear velocity, how fast are you traveling as you run around this circular track? Basically, you're going to use the idea of distance over time. Well, let's focus on one complete circle. If you do one complete circle, the distance you ran is the circumference, which is 2 pi r, and then the time for one complete circle would be the period, which is capital T. So what we're going to do is we're going to take this and we're going to plug it in down here. So now what we have is 2 pi r over period squared equals g mass of the Earth over r. So I can't simplify that in my head, so let's just work it out. G mass of Earth over r, that's going to simplify. So we're solving for period. Let's just solve this for period. So period squared is going to equal 4 pi squared r cubed over g mass of Earth. I would call this done. They would accept that. In fact, I think they say they do on the answer key. Or you could simplify this, you know, take the square root of both sides. That'd be 2 pi r square root r over g mass of Earth. Either one is fine. But that's how you do this part right here. Okay.
Mr. Spalding, why did you square the 2 pi r over t?
Oh, because the equation right here says to square it.
Oh, okay.
I just took this and I plugged it in here, and in this equation, in this equation here, velocity was squared. So when you bring this down, you want to square it.
Okay.
Okay. All right, let's go to the next part. Sorry, I'm trying to make these videos short. I'm guilty of, like, I finished recording these and I'm like, that was 30 minutes. Okay. Number 2, okay, this will be quick. A second spacecraft of mass 2m, so now, you know, they've doubled the mass of the spacecraft, is placed in a circular orbit with the same radius. That's key. This r is the same. And they're asking us about the orbital period of the second spacecraft. Well, the important thing to note here, right up here in our work, right here, notice what happened to the mass of the spacecraft. The mass of the spacecraft, we called that M2. Notice that the mass of the spacecraft canceled out, and that's the answer. So they're saying here, oh, a second spacecraft with double the mass. Well, you're like, well, that's not going to change anything. So the orbital period would be equal to what it was with a satellite or a spacecraft with half the mass, because mass doesn't matter. Basically, the answer here, explain your reasoning. You're going to say the mass of the spacecraft is not relevant. It cancels out in our calculations, or something to that effect. Okay, so let's go to the next screen. So, all right, which brings us to the last part. Okay, so the first spacecraft, how do I hide this? The first spacecraft is moved into a new circular orbit. So the first spacecraft is moved into a new circular orbit that has a radius greater than r, as shown in the figure below. So now they've increased the radius, and this is the first spacecraft, mass m. Is the speed of the spacecraft in the new orbit greater than, less than, or equal to the original speed? All right, so we're going to look to the work that we did before. So the question here is, what happens to the velocity, the linear velocity of the spacecraft, if we increase the radius? So r is being increased. What would happen to the velocity? So let's look at the equation from what we did before. So what we have is, for velocity, where is that? It's up here, so we're going to use this. So the answer is right in there. So velocity is going to be square root g mass of Earth over r, and here's the answer. If you increase the radius with everything else staying constant, we did not change the mass of the Earth or anything. If the radius of the orbit goes up, because r is in the denominator, velocity must go down, which is the answer to the question. So you're going to say the new orbital speed is going to be less than, and then for explaining your reasoning, you're going to say in the equation we derived, r is in the denominator for velocity, so therefore an increase in velocity will cause a, an increase in radius will cause a decrease in velocity. All right, any questions on this one before we go to the next one? This one's all good? All right, well, if there's no questions, I'm going to go to the next one.